This video is designed to teach you about the basic operating principles of fiber optics and how they are used in today's communication systems. You will learn how the various types of fiber optic cables are made and used. You will also learn about the techniques used to connect these cables together to form junctions and splices. It is assumed at this point that you have a solid understanding of electronic principles in both basic and digital electronics. As you will see, for a real-life fiber optic communication system to function properly, it must contain an electronic device to control or modulate the information being transmitted, and an electronic device to convert these pulses of light back into useful information. At this point, we will begin our exciting journey into the field of fiber optics. First, you will see how today's modern optical communication systems were originated. The use of light as a method of communication is not a new idea. For many centuries, mirrors and other shiny objects were used for communication between individuals in remote, isolated areas. By using individual codes, two or more people could communicate between distant locations. This form of communication was very crude and very limited. Next came the use of man-made light and a code system, which was usually Morse code. This enabled groups of people to communicate over a limited distance. The most noted example of this would be the Navy and how they used this system to communicate between ships at sea. However, even this form of communication was very limited. The first major breakthrough for optical communication was brought about with the invention of the ruby rod laser. The ruby rod laser had the ability to generate an intense, coherent source of light which could maintain its small beam size for a much longer distance than the standard light source being used at the time. With the advent of the ruby rod laser, it soon became apparent that some form of a light guidance system would be required to control the use of this new source of light energy if it were to be used for communication. These early experimenters soon realized that the laser beam could be affected by too many obstacles, like rain, fog, clouds, or any kind of structure. When light energy is transmitted, it travels in a straight line. Even though a lens can be made to bend a beam of light, and a mirror can reflect the beam of light, for the most part, light still travels in a straight line. This works fine for many purposes. However, in communication systems, line of sight is not often practical. The light beam must be made to go around obstacles while maintaining its information in a usable form. This brought about the need for fiber optic cables. The early experimenters produced a wide variety of optical waveguides. Hollow metallic tubes were initially considered for use with this new form of light energy. However, there were many drawbacks with this system, and it was soon dropped. This system was followed by the use of small diameter glass fibers, which were bundled together. The glass fibers proved promising, but created two additional problems. First, the light would scatter and escape through the sides of the glass fiber material. Second, the glass was so impure that it would allow only a very small percentage of the light beam to travel through the entire distance of the fiber, even though the fibers were very short. These early fibers had an attenuation of more than 1,000 decibels per kilometer. It was not until 1970 that a fiber cable was designed with an attenuation of approximately 20 decibels per kilometer. This breakthrough brought fiber optic communication closer to becoming a reality. The process used to eliminate the leakage of light from the fiber material was very simple. A two-layer fiber was created. The outer layer was used to keep the light within the glass core of the cable. The outer layer coating was referred to as cladding, and the refractive index of this cladding material was slightly below that of the core material. We will examine how the cladding material is formed later in this video. As the technology of fiber optics increased, fibers were developed in both glass and plastic. This allowed the fibers to become much more flexible. Even though new applications began to emerge with these flexible fibers in the fields of medicine and inspection, one major limitation still remained before these fibers would become suitable for use in communication. They absorbed too much of the light energy, which made attenuation still too high. It was soon discovered that it was not the properties of the glass itself which created the high attenuation, but rather, it was the impurities contained within the glass. By removing the impurities, the engineers theorized that the attenuation of the glass could be greatly reduced. Their prediction proved to be very accurate. Within a few short years, fiber optic materials were developed which would allow direct communication links at distances of over 30 kilometers, or approximately 18 miles. Today's fiber optic cables carry signals for distances of over 50 kilometers. As you will see later in the video, not all fiber cores are the same. Some are made of plastic and some are made of glass. Even though the fibers are flexible, they are still somewhat stiff. Their degree of flexibility will depend on the materials being used and the diameter of the cable. A fiber optic communication system requires more than just a single fiber optic cable to operate. You also need a transmitter at one end and a receiver at the other end. However, for the system to work as a two-way communication system, it must have a transmitter and receiver at each end, as well as two fiber cables. One cable will carry the information one direction, and the other fiber cable will carry the information the other direction. The transmitters and receivers are generally encased in a single package. Before continuing with the fundamentals of optical fibers, we will pause for a short review of the material just discussed. Mankind has used light as a form of communication for centuries. The Navy used lights with shutters for communicating between ships at sea for decades. The first major breakthrough for optical communication came with the invention of the ruby rod laser. Light travels in a straight line. However, it can be bent or reflected through the use of lenses or mirrors. Fiber optic cables were developed because of the need for controlling the beam of light around various obstacles. The first contained optical communication device used hollow metallic tubes to transfer the beam of light. Next, bundles of small glass fibers were used to transmit the information. This, however, created two major drawbacks. The impurities of the glass were so high that only a small fraction of the light entering the fibers was visible at the other end, even with distances as short as 2 meters. The glass also allowed the beam to scatter and exit through the sides of the glass. By reducing the impurities of the glass, the fiber optic cable was able to transfer the beam of light for several thousand meters. The leakage problem was controlled by placing a coating called cladding around the glass fiber core. Fiber optic cables are available in both plastic and glass. A fiber optic communication system requires a minimum of 2 cables, one to transmit on and one to receive on. At this point, you should stop the video and complete Section A of your student workbook. In this portion of the video, you will examine the electromagnetic spectrum and learn how fiber optic cables are made. From a physical point of view, light can be considered as electromagnetic waves or as photons of electromagnetic energy. This light energy travels in a straight line until it is reflected off a surface or until it is refracted from a surface which has a higher index value. To better understand what we refer to as light, we should first examine the entire spectrum of electromagnetic radiation. Light is usually classified in hertz or as a wavelength in meters. In the optical world, however, wavelength is used almost exclusively. The wavelengths used in fiber optic systems are typically measured in micrometers and nanometers. 1 micrometer is 1/1,000,000th of a meter, and 1 nanometer is 1/1000,000th of a meter. As you can see, these wavelengths are very short. By examining the entire spectrum of electromagnetic radiation, you can see that the visible part, which we can physically see, is only a small fraction of the entire spectrum. That light which is visible to the human eye extends from 0.4 to 0.7 micrometers and covers a bandwidth of approximately 320 trillion hertz. Here you see the portion of the spectrum used for optical communication. Notice that at the lower frequency end, it extends into the infrared wavelengths. Also notice that the higher frequency end extends into the ultraviolet region. As the technology for manufacturing glass fibers started to grow, the fibers themselves became more pure, which resulted in a lowering of the attenuation of the fiber core. While these fibers were being studied for their optical response, the presence of low-loss transmission windows were discovered at 850 nanometer, 1.3 micrometer, and 1.55 micrometer wavelengths. The knowledge of these windows represented a large step forward toward the use of fiber optics for communication. The longer wavelengths of 1.3 and 1.55 micrometers exhibited a typical attenuation of approximately 0.2 decibels per 1,000 meters. The only drawback was the expense of producing the cable. While research was being performed on the fiber cables, laser research and development was also being carried forward. The major drawback of the ruby rod laser was that it had to be pumped with an external light source. In other words, a separate light source, like a flash lamp, had to be used to excite the molecules of the ruby rod into producing this concentrated form of light energy. This severely limited the speed with which information could be modulated and sent to the fiber core. A faster method had to be developed. This brought about the advent of the semiconductor laser diode. The first semiconductor laser diodes produced a wavelength of 870 nanometers. Even though this was close to the 850 nanometer low-loss window discovered in the fiber cable, it was still not acceptable. By doping the diode with various impurities and modifying the structure of the diode, it was soon possible to produce devices which could operate in the 850 nanometer, 1.3 micrometer, and the 1.55 micrometer wavelengths. The two major drawbacks of these new and improved diodes were their expense and their short lifetime. This limited their use to long-distance communication. For short communication runs, the less expensive plastic fiber optical cable and low-cost LEDs are generally used. At this time, we will examine some of the factors used to determine which type of fiber cable to use. Not all fiber cables are the same. They have different characteristics and limitations. The reason for the variety of different fiber cables is that their applications are so diverse and often have conflicting requirements. For example, some of the factors which are used to determine the type of optical fiber to use include 1. The maximum bandwidth or speed with which the information can be transmitted through the fiber. 2. The ease with which the cable can be coupled in the field. 3. The ease with which the cable can be spliced in the field. 4. The wavelength of the transmitting device. 5. The physical attributes of the cable to withstand high temperatures and extreme environmental conditions. 6. The flexibility of the cable. 7. The attenuation of the cable per 1,000 meters. And 8. The cost of the cable. There are also other factors which must be considered in specialty applications which are not listed here. As you can see, it would be very difficult to design one fiber cable which would satisfy all these requirements. At this point, we will examine how the cables are manufactured. The process used to produce the fiber optic cables is very precise and highly specialized. The first step in manufacturing the fiber cable is to produce a glass rod called a preform. As you will see in a few minutes, the glass fiber is pulled from the preform rod. Even though there are several different methods used to produce the preform glass rod, the most common method used is called modified chemical vapor deposition, or MCVD for short. The first step in manufacturing the preform rod is to produce a silica tube. This tube will become the cladding of the finished fiber. The silica tube is produced by depositing layers of silica particles and other dopants onto a rotating ceramic form. These particles are deposited with the use of very high temperatures. As the tube reaches its required thickness, it is hardened into a clear glass by heating the tube to approximately 1400 degrees centigrade. After the tube is hardened, the ceramic form is withdrawn from the silica shell. Next, the silica cladding tube, or shell, is placed in a special lathe-type machine. Special gases are then passed through the tube, which results in the core material being produced. The tube is brought to a very high temperature as the gases are sent through it. This causes the gases to form deposits inside the cladding tube, which results in the core material being formed. After the pure glass core has reached the required diameter, the gases are shut off and the preform is superheated. This causes the silica cladding tube to collapse around the core material and form the solid preform rod. The preform rod is then cooled and removed from the equipment. At this point, the solid preform rod is ready to use in the production of the fiber cable. After the preform is made, it is placed into a fiber pooling tower. Here you see a simplified version of such a tower. Notice that the preform rod has been clamped into the pooling tower near the top of the equipment. The end of the preform rod in which the fiber cable is to be drawn is placed into a small furnace which heats the glass to an elastic state. As the filament of glass is drawn from the tip of the preform rod, it is fed through a metering device which monitors the diameter of the fiber cable. The metering device controls the speed of the take-up drum at the bottom of the tower. If the glass fiber becomes too thin, the metering device will slow down the speed of the take-up drum. Since the pull on the fiber isn't quite as strong at the slower speed, the fiber diameter will increase. In the same respect, if the glass fiber becomes too thick, the metering device will cause the take-up drum to increase in speed. This causes the take-up drum to apply more pulling pressure on the cable, which results in the fiber becoming thinner. Next, the glass fiber is passed through a coating device, which places a protective plastic coating over the fiber cable. The plastic coating is used to protect the fiber from outside contaminants and structural damage. From here, the plastic-coated cable is pulled through a curing furnace. The primary purpose of the curing furnace is to solidify the coating on the cable before it reaches the take-up drum. As was mentioned earlier, The speed of the take-up drum actually controls the diameter of the fiber cable while it is being drawn. Here you see a close-up view of the tip of the preform rod while it is in the furnace. Notice that the cladding is drawn or pulled from the preform rod at the same instant that the core glass is pulled. Even though there are other methods used to produce the fiber optic cable, this method seems to be the most popular and is used frequently. At this time, we will stop the video for a short review of the material just discussed. Light energy, as we know it, may be thought of as electromagnetic waves or as photons of electromagnetic energy. Light energy may be classified in hertz or as a wavelength in meters. The visible part of the electromagnetic radiation spectrum is only 0.4 to 0.7 micrometers in frequency width. The portion of the spectrum used for optical communication extends from the infrared to the ultraviolet wavelengths. Low-loss transmission windows were discovered at 850 nanometer, 1.3 micrometer, and 1.55 micrometer wavelengths. The longer wavelengths of 1.3 and 1.55 micrometers exhibited a typical attenuation of only 0.2 decibels per thousand meters of fiber. The ruby rod laser was replaced with a semiconductor laser diode. The semiconductor device did not require a secondary light source to activate the laser beam. This made the device much more efficient. Due to the high expense of the semiconductor laser diode, low-cost LEDs and plastic fiber optic cables are generally used for short communication runs of only a few hundred feet. When choosing a fiber optic cable for a new installation or for replacing an existing one, you must consider the following: the wavelength of the transmitting device, the maximum speed at which the information must be transmitted, the ease with which the cable may be spliced or coupled in the field, the attenuation of the cable per thousand meters, the flexibility of the cable, the tolerance of the cable to temperature and the environment, and the cost of the fiber. Fiber cables are produced by pulling the fiber from a preform rod. A very common method used to produce the preform rod is called modified chemical vapor deposition. Once the preform rod is manufactured, it is placed in a pulling tower where the tip of the preform is heated until it becomes elastic. This allows the fiber to be drawn or pulled from the solid glass preform rod. This concludes review number 2. At this time, you should stop the video and complete section B of your student workbook. In this portion of the You Can Do fiber optic video, you will learn about the use of connectors. Connectors are used to join two fiber ends together. They are also used to join the fiber cable to the receiver or transmitter device. Connectors are commonly used to make temporary connections. However, most fiber connectors are not designed for extensive mating and unmating of the connector. Most connectors are generally only reliable for a few hundred connections. Connectors are usually found at the ends of the communication system where they join the fiber cable to the transmitting or receiving device. Connectors may also be found on patch boxes. The patch box is used when a multi-fiber cable is brought into a building and the cables must be routed to various locations throughout the structure. Connector loss, or attenuation, is an important factor when determining which type of connector to use. Some of the factors which must be considered when choosing a connector are alignment of the fiber access core, spacing between the fibers, the diameter of the core of the cables being joined together, and the reflection of the ends of the fibers being joined. The alignment of the fiber core is very critical. If the fiber core is not perfectly aligned, connector loss could become as much as 20 to 30 decibels. Therefore, the tolerances used when manufacturing the connectors must be very close. The alignment is so critical that most connectors manufactured today are made for specific types of fibers. Since connectors do not actually bond the fibers together, the spacing between the fiber cables or the fiber and the receiving transmitting device is also very critical. This loss can be reduced by using index matching fluids in the connector. This fluid is a transparent gel which closely matches the refractive index of the fiber optic glass itself. Connector losses also occur if the core diameters do not match exactly. For example, if a fiber cable with a core diameter of 10 micrometers is mated to a second cable with a core diameter of 11 micrometers, the loss encountered would be approximately 0.6 decibels. This of course assumes that the light is traveling from the larger core diameter to the smaller core diameter. However, if the light is traveling from the smaller core to the larger core diameter, this loss would become insignificant. Core losses also occur if one of the cables becomes elliptical or out of round. The amount of loss encountered would depend upon the percentage of unmated glass. Reflection loss occurs when light passes between two fiber core materials with different refractive indexes. This loss can be reduced with the use of anti-reflective coating at the ends of the fiber cables. Index matching fluids may also be used to remedy this loss. Another type of loss may occur if the ends of the fiber cables are cut at an angle. The amount of loss encountered would depend upon the size of the angle and how the two ends mated together. Losses can also occur if the fiber ends are not properly polished. When the cable is cut in two, scratches will be present at the end of the fiber. These scratches must be removed. Another common loss occurs when dirt or dust particles become lodged in the connector fitting between the fiber ends. Even though we have listed several types of losses encountered with the use of fiber optic connectors, modern technology has allowed production of inexpensive connectors with losses in the 1 to 3 decibel range. High-performance connectors are also available with losses below 1 decibel. However, these connectors are somewhat more expensive. At this point, we will examine a typical fiber optic connector. Here you see the basic construction of a typical fiber optic connector. As you can see, the connector contains a metal housing, a ferrule to accurately align the fiber ends, and a coupling nut to join the ends together. Now, let's see how to use one of these connectors. Prior to installing the connector, the outer protective plastic coating must be removed to allow access to the fiber core. The coating may be carefully cut off. However, it is usually dissolved with a solvent designed specifically for this purpose. Dissolving the coating reduces the risk of nicking the fiber core and damaging it. Next, the connector body and ferrule are placed over the end of the fiber cable. Depending upon the type of connector being used, the end of the fiber may or may not be cut even with the end of the ferrule. After the length of the fiber has been cleaved, or cut to the proper length, the end of the fiber is polished to a smooth, flat finish. Polishing is necessary to eliminate any irregularities from the surface of the end of the fiber which resulted from the fiber being cut. Finally, the main body of the connector is crimped or glued to the protective coating around the fiber core. Gluing seems to be the preference of many installers. Often heat shrink tubing is used to seal the cable connector junction to ensure that contaminants do not enter the connector. Earlier it was mentioned that the end of the fiber had to be polished to a flat, smooth finish. In optical connector terminology, the term finish refers to the geometry of the ferrule face when the cable is in it. As you can see, there are three common finishes in widespread use with many of today's connectors. They are the flat, domed, and protruding fiber finishes. Here you see a close-up of a flat finish ferrule. Notice that the top of the ferrule is flat and that the fiber core is flush with the end of the ferrule. This style ferrule is widely used due to its simplicity, low cost, and ease of use. The major disadvantage of the flat finish ferrule is that intimate contact between the two fiber ends is very difficult to achieve. This is due to the fact that the face of the ferrule is usually not perfectly flat. Even with the tight tolerance used by the manufacturers, making every ferrule perfectly flat and perpendicular is almost impossible. Here you see a close-up of the dome finish ferrule. The dome finish ferrule overcomes the disadvantages of the flat finish ferrule by reducing the contact area of the face of the ferrule to the area which immediately surrounds the fiber core. When contact occurs, only the crown of the dome mates to the receiving connector. The material most commonly used to produce the dome finish ferrule is zirconia. Zirconia is soft enough to be shaped even though it is a very hard ceramic. Zirconia also has the ability to flatten a very small amount when the optical connection is made. This allows for a much better contact between the fiber ends. Dome finish ferrules are commonly used for single mode applications only. Here you see a close-up of the protruding fiber finish. This style finish reduces the ferrule contact even more. As you can see, this style finish allows the fiber to protrude from the face of the ferrule by approximately 1 to 3 micrometers. This ensures that the fiber ends are the only areas of contact when the ferrules are mated in a connection. These connectors are inexpensive, easy to install, and can be done in the field. Because of the special tools required and the tight tolerances, more and more cables are being cut to customer-specified lengths and the connectors are being installed at the factory. This makes the installer's job much easier. Before continuing with couplers and splices, we will pause for a short review of the material just discussed. Connectors are used to make temporary connections between two fibers, or between a fiber and a receiver or transmitting device. The four primary factors which affect the losses encountered in fiber optic connectors are alignment of the fiber core, spacing between the fiber ends, the diameter of the fiber cores, and the reflection of the ends of the fibers. Index matching fluids are commonly used to reduce losses encountered in spacing, alignment, and reflection. Prior to installing a connector, the protective coating must be removed from the fiber cable. This is usually accomplished with the use of special solvents. After the fiber core has been exposed, the body connector and ferrule are placed on the cable. Next, the end of the fiber is cleaved to the proper length for the connector style being used. The end of the fiber is then polished to a flat, smooth surface. Next, the metal part of the connector body is crimped or glued to the protective coating around the fiber core. Finally, heat shrink tube is used to seal the cable connector junction. This reduces the chance of contaminants entering the connector. The three most common types of ferrule finishes are flat, domed, and protruding fiber. This concludes review number 3. At this time, you should stop the video and complete section C in your student workbook. In this portion of the video, we will discuss fiber optic couplers. The one primary difference between the coupler and the connector you just studied is that couplers are used to join 3 or more fiber ends together. Couplers are classified as being active or passive. We will begin with examining the passive coupler first. Here you see a passive T-coupler. As you can see, the T-coupler has 3 ports. T-couplers are commonly used to connect input or output devices to a data cable which is carrying the optical information. Here you see a directional passive T-coupler. Internally, the T-coupler is designed to split the incoming optical signal into the 2 remaining ports. Since the light energy is split, the total output from each of the 2 output ports can never be larger than the incoming data source. Notice that when the light enters the in port, it divides the light energy between the out port and the device port. Now notice that when the data light source enters into the output or the device port, that the light does not split between the 2 remaining ports. It only travels out the input port. Therefore, for this coupler to function properly, the optical data must enter through the correct port. In most situations, the incoming power will not divide equally between the output ports. This fact must be taken into consideration when designing a fiber optic communication system. Here you see a bidirectional passive T-coupler. Notice that with this coupler, the optical data can enter any one of the 3 ports and exit the other 2. This simple coupler allows the optical data to reflect from a mirrored surface placed at the back of the coupler. The light signal is then directed to the 2 remaining ports. Here is another passive T-coupler called the wavelength selective T-coupler. In this particular device, a glass plate is used to separate the beam into its different wavelengths. This is accomplished by coating the glass with a special coating which makes the glass transparent to certain wavelengths while reflecting all others. Here you see another passive coupler design which allows the user to connect 4 or more fibers together. It is referred to as the star coupler. It is common to find this coupler with several dozen ports. These couplers are designed to have a given number of input-output ports. The method used to designate the number of inputs to outputs is very simple. A 2x8 would have 2 inputs and 8 outputs. An 8x8 would have 8 inputs and 8 outputs. A 64x64 would have 64 inputs and 64 outputs. The first number represents the number of inputs, and the second number represents the number of outputs. Here you see a simple 2x2 passive star coupler. Notice that if the optical data enters either port A or port B, the optical data will split and exit both ports C and D. You may have also noticed that this style coupler is somewhat bidirectional, in that the signal can also enter ports C or D and exit ports A and B. By fusing the fiber cores together, you can create a star coupler with a multitude of input and output ports. The number of output ports is only limited by the amount of light energy being made available from the input. Remember, the light divides in a passive device. Therefore, only small amounts of light energy can be made available for each output port. Most star couplers are designed to be used with multi-mode fiber cables instead of the single-mode types. Now let's examine the active coupler. Active couplers contain a receiving device, a control stage, and 1 or more transmitters. The transmitters are used to boost the incoming signal to its original strength. Let's examine a simple active coupler and see how it works. Internally, the active coupler contains a detector stage, a low noise amplifier stage, a power stage which acts like a switch, and a transmitting device for each port. The theory of operation for these devices is very straightforward. First, the detector stage receives the optical data and converts it into electrical energy. This electrical energy is then passed through the low noise amplifier stage where it is increased in magnitude. This stronger signal is then used to control the power stage, which works like a switch. This stage has two modes of operation: cutoff and saturation. The power stage then turns the transmitting devices on. When the LEDs or laser diodes are turned on, they emit electromagnetic energy into the output ports. Here you see a simplified schematic of an active coupler. We will examine this circuit to gain a better understanding of its principles of operation. The input fiber cable carrying the optical data is connected to the coupler in such a way that the cable is optically in line with the detector cell. When the optical data reaches the detector device, the detector changes its value of resistance, which causes the low noise amplifier stage to become unbalanced and produce an output. When the base of the power transistor receives the bias voltage from the op-amp stage, it turns on to full saturation. The resistor in series with the transistor is merely a current limiting device for the LED outputs. When the transistor swings into saturation, it allows the current to flow through the LEDs. As you noticed, the LEDs are connected in parallel to the collector of the power transistor. When the LEDs turn on, they emit a new, more powerful electromagnetic energy into the output ports of the device. Here you see a typical scenario in which an active coupler would be used. Notice that 100% of the light energy is being sent to the first T coupler stage in the communication system. Since we already know that light must split in a passive coupler, we will assume that the light divided equally between the two ports as it proceeds through the first coupler. This allows 50% of the light energy to exit the first coupler stage. This 50% then travels through the second passive T coupler. Once again, the energy splits, half going out one port and half passing through the coupler to the next stage. At this point, we have only 25% of the original signal remaining. This 25% then enters a third passive coupler, where it is again split in two. This only allows 12.5% of the original optical data to be sent to the next stage. Since our next stage is an active coupler, it takes this weak optical data and reconstructs it back to its original strength. These stronger signals are then sent to other devices connected to the communication system. You should have noticed by now that the active coupler requires both optical data as well as electrical energy for proper operation. You should also have noticed that the active coupler is strictly a directional device, in that the output ports cannot be used as inputs, nor can the input be used as an output. We will now pause for a short review of the material just discussed. Connectors are used to join two fiber ends together. Couplers, on the other hand, are used to connect three or more ends together. Couplers are classified as being either passive or active. The primary difference is that active couplers require electrical power to operate. Passive couplers may be classified as being directional or bidirectional. Star couplers are used when several fiber ends must be joined together. Active couplers are used to regenerate weak incoming optical data signals back to their original strength. This concludes review number 4. At this time, you should stop the video and complete section D in your student workbook. In this portion of the video, you will examine fiber optic splicing. Unlike the connectors and couplers just discussed, splices are used to make permanent connections between fibers. As you will see, splices are commonly made by welding or gluing the fiber ends together. The welding process is commonly referred to as fusing. Since splices make permanent bonds between the fibers, they are most often found in the outdoor environment. Connectors and couplers, on the other hand, are commonly only used for indoor applications. With today's modern equipment, splicing is very easy and fast. There are fusion splicing machines available which make it so easy that anyone can perform this simple task. Now let's examine how a splice is made utilizing the fusion technique. First, the ends of the fiber cables must have their protective coatings removed. This exposes the bare fiber cores. Next, the fibers are cleaved to the proper length and polished. Then the bare fiber cores are placed into the fusion splicing machine where they are aligned and gapped to the proper setting. Once the fiber cores are set, the fusion process takes place. Basically, a thermal arc is used to melt the ends together. As you can see, the two ends have become one solid piece. Finally, a form of heat shrink tube is placed over the splice. This protects the splice and gives the cable some added strength. It was mentioned earlier that splices can also be made by gluing the fiber ends together. This also makes a permanent connection. However, the cable loss is somewhat higher. This form of splicing is often called mechanical splicing. Mechanical splicing is most often used with multimode fibers. The one major advantage of the mechanical splice is that it does not require expensive splicing equipment. Here you see a V-groove splice connector designed for 5 fiber cables. Its theory of operation is very simple. Before the fiber cores are placed into the V-groove connector, either index matching fluid or epoxy is placed into the grooves. This reduces the reflection loss in the splice connector. After the index matching fluid or epoxy is placed into the grooves, the fiber cores are placed into the V-grooves and then butted together. The V-grooves center the fiber cores, regardless of any slight variations in the core diameters. It should be noted at this point, though, that only those fiber cores with matching core diameters should be mated. Next, the top of the connector is placed over the fiber cables and is sealed into place. As you can see, mechanical splices are very easy to perform and can be done easily in the field. The typical loss of a mechanical splice is approximately 0.25 decibels for multimode fibers. At this time, we will examine the theory of operation of the transmitting and receiving devices found in the fiber optic communication system. We shall first examine the transmitter. To this point in the video, we have only shown the transmitter as being either a laser diode or a light-emitting diode. However, the transmitting device contains many more sections than merely the output device which generates the optical energy. Here you see a simplified transmitting device. Notice that it contains an encoder stage, a switching stage, a driver stage, and an output stage. We will examine each of these stages one at a time. The encoder stage receives the incoming electrical data and converts it into a serial data format. The information, or data, is still in electrical form at this point. The serial data is then fed into the switching stage for further processing. The switching stage performs two major functions. First, it contains a timing control circuit, which sets the on-off duration of the driver stage. Second, it also contains a wave shaping circuit, which assures that the slew rate of the on-off pulses is held to a minimum. From here, the electrical data is sent to the driver stage. The sole function of the driver stage is to provide current to the output device. The speed with which the driver stage can swing from cutoff to saturation and from saturation to cutoff will ultimately determine the maximum data rate of the transmitting device. Finally, the current from the driver stage is fed into the output device. For short runs of only a couple hundred meters, The output device will generally be an LED. For distances of several thousand meters, the output device will be a laser diode. As you can see, the operation of the transmitting device is very simple and straightforward. It receives the input data in the form of electrical pulses, converts these pulses into a serial string of data bits, times and shapes the data bits, and then turns the output device on or off in relationship to the incoming data being received. The output device converts the electrical information into optical information, which is then transmitted through the fiber optic cable. Now let's examine a typical receiving device. Notice that the receiving device is somewhat similar to the transmitting device we just discussed. This device contains a detector stage, a switch amplifier stage, and a decoder stage. Now let's examine each of these stages. The detector stage consists primarily of a photodetector with some form of optical lens. The detector stage is generally made sensitive to a particular bandwidth of frequencies. When the optical data reaches the detector, the resistance of the detector will change, thereby producing a current which is fed into the switch amplifier stage. The switch stage may or may not contain an amplifier section. However, it will generally contain a timing control circuit and a wave shaping circuit. The timing section places the data back to its original data rate. Next, the signal is sent to the decoder stage, where the electrical data is routed to the input of the equipment receiving the transmitted data. As you can see, the receiver accepts the optical data at the detector stage. The detector stage then converts the optical data into electrical energy pulses. These pulses are then timed and shaped in the switching stage. From here, the electrical data is sent through the decoder stage to the equipment receiving the information. We will now pause for a short review of the material just discussed. Splices are used to make permanent connections between fiber ends. Splices are generally used outdoors, while couplers and connectors are generally used indoors. The two most common types of splices are fusion and mechanical. Fusion splicing actually melts the fiber ends together. Mechanical splicing does not fuse the fiber ends together. Instead, an epoxy is generally used to hold the fibers in place. Transmitters are designed to convert electrical data into optical data. Receivers, on the other hand, are designed to convert optical data into electrical data. This concludes review number 5. At this time, you should stop the video and complete section E in your student workbook. By now, you should have a basic understanding of fiber optic cables, their connectors, couplers, splicing techniques, the transmitters, and receivers. To retain this knowledge on fiber optics, we recommend that you view this video often.